Welcome back to COSC 2325. This is Chapter 6, Conditional Processing. Okay, in this chapter, but in this section of this video, we're going to cover Boolean instructions. We're going to review the CPU status flags and what they do. We're not going to review all of them right now. We're just going to review some of the ones that we'll be looking at immediately. We'll look at the AND instruction, the OR instruction, XOR, NOT. We'll look at several applications where we can actually use these Boolean instructions. And then we're going to look at the test instruction. Okay, so here's a review of the status flags. The 0 flag is set when the result of an operation equals 0. So remember, this is a mathematical operation, like if you add or subtract and the result of that addition or subtraction gives you a 0. Then the carry flag is set when an instruction generates a result that is too large. So the result is too large or too small for the destination operand. So, for example, when you're adding two large numbers and that result cannot fit into the destination register, that carry, the flag is going to be set. So it's going to carry into the most significant byte. And so remember that if you're looking at zeros and ones, the most significant byte is going to be, if we're looking at this, this right here is your most significant byte, and this is your least significant byte. So if we're adding two binary numbers, and when we add the very last two most significant bytes, if it carries outside of the number, then we've set the carry flag. And all you have to remember is that if the two numbers that you're adding, or maybe one of them is added to the other one and it's just too large for the destination register, then we're going to carry. When subtracting, if we subtract a smaller number from a larger number, so for example, if we subtract a smaller number from a larger number, we borrow into the most significant byte. So let's say that we say subtract 6. So we say subtract 6 from 5. We're going to borrow into that most significant byte. Also, we do carry flags when we do byte-wise shifts, which we'll talk about in this chapter. So when we shift our bits over, if we carry into most significant byte, we carry out of it, then we would set the carry flag. Then we have the sign flag. It's set if the destination operand is negative, and it is cleared if the destination operand is positive. Remember that so to set the flag, we set it with the 1, and to clear it, we clear it with a 0. Set with the 1, cleared 0. The overflow flag is set when an instruction generates an invalid signed result. So if you have a signed integer arithmetic, so let's say that you're adding two signed numbers and the result is too large or too small for that data type range, then you would get assigned, you get an overflow flag. So for example, if you have assigned byte, so assigned byte has a range of -127 to +127. That's the range. Let me just double check that assigned byte range, just to make sure I have that correctly in my head. No, -128, so this is an 8, to +127. So this is the range. So if you do some signed integer arithmetic and you're dealing with a byte, if you get a -129 overflow flag gets set, or if you get a +128 or a bigger number, the flag is set. If you're dealing, if the register that you're dealing with is byte size. Okay. So let's take a look at this AND instruction. So this is a Boolean instruction. In assembly, it operates, this AND instruction operates on binary values, and it compares the bits of the two operands. So in assembly, we're looking at two binary numbers, and we're going to compare each bit. So we compare that bit, and we're going to compare these two bits and these two bits, etc. So we're looking at two binary numbers. The result is a new value, so this would be the new value here, where each bit in the output is set to 1 only if the corresponding bits in both operands are 1. If any bit is a 0 in either operand, the result is a 0. So a 1 and a 1 is going to give you true. So notice the only time that you're going to get a true or a 1 is if you both are 1. Everything else is going to give you 0 or false. So I'm looking right now at this right here. So the only thing that gives me a 1 is a 1 and a 1. So here we have 1 and 1 gives me 1. 1 and 1 gives me 1. 0 plus 0 and 1 gives me false, because one of them is a 0. Here both are 1, so this stays a 1. This has a 0, this has a 0, this has a 0, this has a 0. So all these are zeros or cleared out. So what you notice, let me erase all this here. What we notice in this example here is that this side was unchanged. So notice that this is the answer right here that gets, or the result. So by doing an and having all 1s in these 4 bits, it allows for these to stay the same. And you have 0s on this side. That's going to change every one that you have in your in your source is going to change to zeros or cleared. And we're going to look and see why or how we use this in an example. So if I have 1, 1, 0, 1, okay, so, and then let's say that that is in a certain register. Let's say that's in register AL, for example. And then I do and oops, AL. So here's AL. So AL is going to be my destination. That's going to be the top number. And then I'm going to and what I want to do is I want to clear AL. I want AL to be cleared to all zeros. So the way that I can clear AL to all zeros is ANDing it with all zeros. So 1 and 0 will be 0, 0 and 0 will be 0, 1 and 0 will be 0, 1 and 0 will give me 0. So now AL will get changed to all zeros. So 1, 1, 0, 1 are going to go away and get changed with all zeros. So that's one way that I can clear my registers, by ANDing my register with all zeros. And if I don't want to make a change, as you saw down here, I would then AND it with all ones. Right there. So here's another example. I have, so here we've done a move into AL, and we've moved this binary number into AL. Then we've moved this binary number into BL. And then we've AND AL and BL. Remember, the answer or the operation is going to end up saving in AL. So 0 and 0 are going to give me, so we're looking at the very first byte, which is byte 0. 0 and 0 give me 0. 1 and 0 give me 0. 0 and 1 give me 0. Remember, the only time I'm going to get a 1 is when there's two ones. Here's two ones right here, so now I'm going to get a 1. So in this one, I'll have a 0, so I'm going to make that a 0, I'm going to make that a 0, I'm going to make that a 0. And the very last or most significant bit is 1 and 1, which give me a 1. So this is an example of what we called bit masking, and bit masking just clears or sets to 0 the bits where the mask has zeros. So the mask here would be BL. BL is the mask. Let me erase this right here. So BL would be the mask right here, and it clears or sets to 0 the bits where the mask is 0. So we're going to mask these two bits, and we're going to mask these two bits right here. The AND instruction is used for various purposes in assembly language, including clearing specific bits in a value by using a mask. We're going to look at this example 1 in a real life application. Checking the status of individual bits in a register or in memory. So you can check the status, is the bit turned on or is the bit turned off? And then setting specific bits to 0 while leaving others unchanged, just like we saw in our previous example. Alright, so this is the OR instruction. So with the OR instruction, it's opposite of AND. Everything is true. So everything gives us a 1 except when both the destination and the source are 0. So we're performing a Boolean OR operation between each pair of matching bits in two operands. Here's operand 1, the destination, operand 2, the source. By the way, the operands are the same as the move type operands. So in your destination, with the move, remember you could have a register or memory, and then the source could be a register, a memory, or a constant. So in this example, we have our very first 2 bits are 1, so 1 or 1 gives us 1. Remember, we're going to get all 1s unless we have 2 zeros. Then we have 1 or 1 gives us 1, 0 or 1 gives us 1, 1, 1 gives us 1. The only time that we're going to get zeros is going to be the very last 2 bits, which are both zeros, and that gives us zeros. So that's with the OR statement, or the OR instruction. Then the XOR, you're going to, looking over here at the chart on the right, you're going to get 0 if both operands are 0, or both bits are 0, or both bits are 1. So basically you're looking at the operand's bits, and if they're equal, then we set to 0. So in this example, bit 0, 1, 3, 6, and 7 are all equal. So those are the only ones that are set to 0. 0, 1, not 2, but 3 is, not 4, not 5, but 6 and 7 are set to 0. So you're looking for bits that are the same. If they're the same, either equal to 0 or 1, then we change that bit to 0. Remember that this value down here is going to be saved in the destination right there. Whatever that destination is, whatever register you put there, that's where it's going to be saved. Or it could be a memory location. XOR is a useful way to toggle or to invert the bits in an operand. The NOT instruction is just very simple. It's just going to take each bit and convert it to the opposite bit. So if you have a 1, converts it to a 0, changes it to a 0. So we're just inverting all the bits. 1 becomes 0, 1 becomes 0, 0, 1. So they just all get inverted. Okay. This here's just a chart that I added to give you a summary of all the instructions. Actually, I haven't gone over the test instruction yet, but with the AND, it returns 1 only when both bits are 1. Otherwise, it always returns a 0. NOT is going to reverse all the bits, or it's going to return a 1 if one of the 2 bits or both of the bits are 1. And the only time that you're going to get a 0 is if both bits are 0. So here you, with the OR, remember if both bits are 0, you get a 0. Here, if both bits in the AND, if both bits are a 1, you're going to get a 1. And then the XOR returns a 1 only if one of the 2 bits is a 1. Returns a 0 in all other cases. So it returns a 0 if it's 0, 0 or 1, 1. So 0 XOR 0 is a 0, 1 XOR 1 is a 0. Both of these are going to be 0. And then we're going to look at the test. So the test instruction is going to be just like the AND instruction, except it doesn't affect your first operand. It's like you test it with the AND, but you don't make any changes to that register or memory location in that first operand. So I wanted to show you this ASCII table because in the next slide we're going to be looking at capital A, the binary number for capital A, and the binary number for lowercase a. So let me find lowercase a here. So if you take a look at the binary number for capital letters and lowercase letters in the ASCII table, you'll notice that bit 5 is the only bit that's different between those two binary numbers. So here's bit 0, both are 1. The next 3 bits are 0. So 0, 1, 2, 3, 4, 5. This is a 0 in bit 5. This is a 1 in bit 5. And that's the only difference between capital letters and lowercase letters. So what we're going to do next is we're going to convert a lowercase letter. So here's lowercase a. We're going to convert that lowercase letter to a capital letter by using the AND instruction. Okay, so the lowercase letter in binary is this number right here. And I broke it out into 4 bits, so it's just easier to read. They're not running together. And then to switch that bit in position 5, you're just going to have all 1s, and in position 5 you're going to have a 0. And what that's going to do is going to switch the bit for us. So we're going to AND with this operand right here, and by having all 1s in bits 0, 1, 2, 3, this stays the same as the original. So 1 and 1 is 1, 0 and 1 is 0, 0 and 1 is false, 0 and true is false. Same thing here, 0 and 1 is false, 1 and 0 is false. So here's that bit number 5. So that's the bit 5 that got changed. So it used to be a 1, now it got changed to a 1. Bit 6 and 7 stayed the same. So to convert your lowercase letter to a capital letter, all you have to do is use the AND instruction to clear bit 5. And remember, when we say clearing a bit, it just means make that bit a 0. So if I say clear bit 1, we'd have a 0 in bit position 1, and everything else would be 1s. Remember, this is bit position 0, bit position 1, bit position 2, 3. So on and so forth. So if I say clear bit position 1, then put a 0 in that position 1. If I say clear bit position 3, then only that one should be a 0. 0 is what clears it out. And you're going to use the AND instruction to clear it, or to change it. Okay, in this slide, we're going to convert a binary decimal byte into its equivalent ASCII decimal digit. So the number 6 is written like this in binary. Remember that if you're converting a binary to a decimal, position 0 has a value of 1, because you're saying 2 to the power of 0. 2 to the power of 0 is 1. And then here's 2 to the power of 1. Sorry, 2 to the power of, 2 to the power of 1 is 2. And then this is 2 to the power of 2. 2 times 2 is 4, so this is 4. This is 8. So to convert this to a decimal number, I would take that 1 and multiply times a 0, and I get 0. 2 times 1 is 2. 4 times 1 is 4, and you're adding 2 plus 4. So 2 plus 4 is 6. All these are 0, so we're not going to mess with those. So this has a decimal value of 6. Right? Because 2 times 1 is 2, plus 4 times 1 is 4. You add it together to get 6. So this is the decimal value in binary, but in the ASCII table, if you go back to the ASCII table, this is the binary number for the digit 6, because in the ASCII table, it's not the decimal 6, but the character 6. Which is two different things. So the decimal value is a different value than the character 6. That's why you see these single quotes here, because we're talking about the character, not the decimal. Okay, so if you have the decimal value 6, and this is the binary number here on the right, I've rewritten it here. The way that you can convert this decimal 6 into the character 6 is by ORing the instruction set with the bits 4 and 5. So this is bit 0, 1, 2, 3, 4, 5. So we're looking at these 2 bits right here. And what we're going to do is OR and make those 2 1s. So we'll OR 0, 0, 1, 1, and the rest 0. Remember, when you do an OR and you have a 0, it doesn't change the value of your original operand. So 0 or 0 stay 0, 1 or 0 stay 1, 1 or 1 stay 1, 0 or 0 stay 0. So these first 4 numbers are unchanged. But once you OR with a 1, it actually changes your value. So a 0 and a 1 changes that to a 1, position 4, and then position 5, 0, and 1 change to a 1, and the rest get unchanged. So if you're wanting to convert a binary decimal byte into its equivalent ASCII decimal digit, you would OR and put a 1 in the 4th and the 5th position. So right here. Okay, in this example, we're going to jump to a label if an integer is even. So we want to jump to some label if the integer is that we have is even. In this example, we have word val, and we move word val into AX. So it has some number. We don't know what that number is, but it's inside this variable, word val. Then we take and we use and we AND AX with a 1, which means that we're ANDing the lowest bit with a 1, and if the result is 0, the number is an even number. So let's say that we have 0, 1, 1, 1, and then we AND with a 1. 1 and 1 is still a 1. So all of these right here, this is going to be 0, 0, 0. So 1 and 0 will be 0, and then 1 and 0 will be 0. So these are all zeros. And because they're all zeros and this is an AND, all these are going to be zeros. So it said if the lowest, we AND the lowest bit with a 1, is the result a 0? Well, no, the result wasn't 0. The result is a 1 here in the lowest bit. So to get a 0, we'd have to have all these bits to be 0. Since it's not a 0 for this particular number, then the number is not even. It's an odd number. So let's see if that's true. So remember, this here is a 1, a worth 1. This is worth 2. This is worth 4. This bit is 8. So we multiply 1 times 1 is 1. 2 times 1 is 2. 4 times 1 is 4. So I'm going to add these three numbers. So 4 plus 2 is 6, plus 1 is 7. Well, 7's not an even number, and that's why I got a 1 right here. So then I have this new instruction that we are introducing, JC, which means jump on 0, or jump if 0. So and then this is just a label. Even value is just a label. So it's a jump. If the 0 flag is set, then go ahead and jump to this value. So if the 0 flag is set to a 1, then we would jump there. So this application says jump to a label if the value in AL is not 0. So jump if not 0 is just an instruction J and Z. So J and Z is just jump if not 0. And then to do that, we would use the OR. So you OR the bytes with itself, and then use J and C if it's not 0. So let's say that AL is 1, 1, 0, 0. So that's AL. And then if you do an OR like this, and you OR with the same value, 0 or 0 is going to give me 0, of course. 0 or 0 is going to give me 0. this is a true, so true and true, we know it's going to be true, and true is going to be true. So we want to jump to a label if the value NL is not 0. Well, of course, we know the value in AL we said was this right here. This is definitely not 0. This is 1, 2, 4, 8. So only these 2 bits are 1, so 8 plus 4 is 12. So this is the decimal value of 12. So if we had, if AL was all zeros and you do 0, 0, 0 or 0, 0, 0, you're going to get 0, and then you could jump if it's not 0. Oh, sorry, this is jumping if it's not 0. So yes, this would definitely jump because it's a number 12. So jump if it's not a 0. And so you could do this. You could actually have the user enter these numbers. So let's say the user enters the number 12 and you're wanting to check, did the user enter a 0? You could use these instructions. If the user enters a character and you want to convert that character to lowercase or uppercase, or let's say they enter a lowercase, you want to convert it to uppercase, you could use the instructions that we did earlier. So with all these example applications that I've shown you so far, this would be if the user gives you that input and then you want to check the input that they've, the value that they've entered, or the character that they've entered. So we wouldn't hard code it like, we wouldn't hard code a number. Okay. So here at the bottom, it's just saying ORing any number with itself does not change its value. So whenever you OR a number with itself, it does not change the value. Okay, next slide. Here's the test instruction. Again, it performs an AND operation, but it just doesn't change the destination. So no operands are modified, but the 0 flag is affected. So for example, this says jump to a label if either bit 0 or bit 1 in AL is set. So this would jump in non-jump if not 0. It would jump to this value right here. But because we did test, AL does not get changed. So we're testing it. It's doing an AND, but AL is not affected. Okay, the next slide. This code snippet is used to check whether the 2 rightmost bits of the AL register are both 0. If they are, so it's checking if we have AL, and in AL, let's say for example, you have this here, this number, let's just do 2 zeros. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bits, which is 1 byte. And then we're looking at the 2 rightmost bits right here. So we're saying this is AL. So if both of these are 0, then it jumps to this label right here. If only one of them is 0, it does not jump. So if maybe this one is 1, then it does not jump to this label. Okay, that's the end of this section for chapter 6. In the next section, we'll start looking at compare, and we'll look at other jump instructions and other conditional statements.